Assalamu alaikum. Physical Geology, Chapter 11, Crustal Deformation and Mountain Building, presented by Khalid Namrouni, PhD in Geology from Texas A&M. And Khalid Namrouni is a staff member at the Department of Earth Sciences, Yunus University, Benghazi, Barga State, or Cyrenaica State. The reference used for this talk is Essentials of Geology. This is the Department of Earth Sciences at Yunus University, and this is the main entrance of Yunus University. This is the Prince Idris Sanusi, Prince of Barga State or Cyrenaica State. And here's the flag of Barga State behind Prince Idris. This is the capital of Cyrenaica State, Benghazi. And this is the chief commander of the Sanusi army, Omar al-Mukhtar. And this is the map of Barga State or Cyrenaica State. Outlines: deformation, folds, faults, and joints. And then we'll look at stress, compressional, tensional, and shear stress, three types of stress. Strains, which is the response of the stress, elastic, brittle, and ductile deformation. Factors that affect rock strength, temperature, confining pressure, rock type, and time. Folds, we have anticlines, synclines, monoclines, domes, and basins. Folds, dip, slip, faults, normal, horse and graben, reverse, thrust. And then we have strike, slip, faults. We call them transform faults. And then we have joints, mountain building, and then principle of isostasy. So what causes rock to deform? Deformation is, we have a lot of definition by the way here. Deformation is a general term that refers to all changes in the shape or position of a rock body in response to stress. So if you apply stress on any rock, any changes happen to that rock, we call them strains, so the response. Rock structures or geological structures are the features that result from forces generated by the interaction of tectonic plates. So, in general, all of these geological deformations happen due to plate tectonics. So, plate tectonics is the main drive behind that. Includes folds, faults, and joints. So stress is the force that deformed rocks. When stress acting on a rock exceeds its strength, the rock will deform by flowing, folding, fracturing, or faulting. The magnitude is a function of the amount of force applied to a given area. So force applied to an area, that's called magnitude of the force. And stress applied uniformly in all directions, we call confining pressure. So confining pressure, the pressure applied from all directions is even, the same amount. But if the pressure from stress applied unequally in different directions is called differential stress. So differential stress is not uneven. It has some sides stronger than the others. So we have two different types of stress here: confining pressure and differential stress, or differential pressure. Types of stress. As we said, we have three types: compressional, tensional, and shear. Compressional stress squeezes a rock and shortens a rock body. So what it does? Squeezes the rock, compress it, and shorten it. Tensional is the opposite of the compressional. Tensional stress pulls apart a rock unit and lengthens it. So this is tensional causing lengthening, but compressional shortening. Shear stress is a different. Produces the motion, so there's a motion here similar to the slippage that occurs between individual playing cards when the top of the stack is moved relative to the bottom. So let's look at this. So if we imagine we have a card stack, when we move the top of it, imagine there was a circle here. When we move the top of it, this circle will change into ellipsoid. So this is the the third type of stress, which is shear stress. And this ellipsoid is used to measure the amount and type of the strain that happened due to the stress. Let's go back and see the strain. So when we apply pressure, stress on any rock, if the rock changes it or deform it, we call strain. So the strain is the answer or the result of the stress. Strain is change in shape caused by stress. And what type of stress? By differential stress, mostly. So strained bodies lose their original configuration during deformation. How? We'll have elastic, brittle, and ductile deformations. We have three types of deformation. Elastic deformation, the rock returns to nearly its original size and shape when the stress is removed. So the rock can go back, the rock or the material that we applied stress on or at will return back to its original size and shape when we remove the stress. But once the elastic limit or the elastic strength of a rock is surpassed, the rock is either bends, we call ductile deformation, and this causes falls, or breaks, we call it brittle deformation, and this causes falls. Usually bending happened at greater depths, and the brittle deformation or the breakage happened at shallower depths on the Earth's surface. Okay, how do rocks deform? Factors that affect rock strength: temperature. So higher temperature rocks deformed by ductile deformation, and that, as we said, it happened at greater depths, below their surface. Whereas cooler rocks deformed by brittle deformation. Usually cooler rocks existed at their surface. Confining pressure. Confining pressure squeezes rocks, making them stronger and harder to break. Rock type, the third factor. Crystalline, example, crystalline igneous rocks generally experience brittle deformation. So igneous rocks, because they're crystalline, they deform it. They have brittle deformation. Whereas sedimentary and metamorphic rocks with zones of weakness generally experience ductile deformation. So they bend, folded. Okay, time. Forces applied over a long period of time generally result in ductile deformation, results in bending, not fracturing, most of the time. Okay, here we got two faults, which is the bending, ductile deformation. Faults, rock structures formed by ductile deformation. So during crustal deformation, rocks are often bent into a series of wave-like undulations called faults. What's the characteristics of these faults? Most faults result from compressional stress. That results, or stresses that result in a shortening and thickening of the crust. What types of faults we have? Anticlines and synclines, for example. Anticlines are upfolded or arched sedimentary layers. There is a main characteristic for the anticlines. All the strata or all layers are in the center, at the center of the anticline. Synclines are downfolded or troughs of rock layers. What's the main characteristic of synclines? Younger strata are in the center. So anticlines, older strata in the center, synclines, younger or youngest strata in the center. Also, we have more classifications about anticlines and synclines. Depending on their orientation, anticlines and synclines can be described as symmetrical, asymmetrical, overturned, or plunged. So symmetrical. The limbs of the fold are mirror image of each other. So they're similar, both sides. Asymmetrical, the limbs of the fold are not identical. Overturned or recumbent, one or both limbs are tilted beyond vertical. Plunging, the axis of the fold penetrates the ground. So let's look at figures to understand what we're talking about. So here we have a series of anticlines, synclines, anticlines, synclines, but these anticlines are different. So if you look at this first anticline here, there's a figure we call symmetrical fold or symmetrical anticline. If we have axial plane along the fold axis, this is the fold axis, and we cut it with an axial plane, we'll find the limbs at both sides like image mirror. They look like each other. But asymmetrical, if we have an axial plane going through the fold axis, we'll find one limb is different than the other. So this is asymmetrical. And if one of the limbs turned beyond 90 degrees, we'll get the overturned. So this limb here, it's overturned. This is the axial plane, and here we have overturned limb. So this is overturned fold, this is asymmetrical fold, this is symmetrical fold. Three types of anticlines. And here we have synclines too, by the way. Anticline, syncline. Sides of the anticline or syncline, we call them limbs. And this is the fold axis. So we go to the plunging. As we said, we have a fold axis. If this fold axis penetrates the earth, it's not horizontal like here. We have penetration. In this case, we call it plunging fold. And plunging folds, they have nose. If you look at them from aerial photograph, you will see this nose. So if you look at this example here, we have this nose that tells us there's a plunging fold, and this is the direction of plunging. And these rocks, they said, oldest rocks are in the middle and youngest outside. So if the oldest rocks at the center, that means this plunged fold is anticline, plunged anticline. Folds, rocks, rock structures formed by ductile deformation. Okay, we have other three terms, domes and basins. Domes are upward circular feature, and exactly the same characteristic as anticlines. Domes, oldest rocks are in the center. Basins are downward circular features, and their youngest rocks are in the center. So domes, they have oldest rocks in the center like anticlines. Basins, they have youngest rocks in the center like synclines. We have monoclines. Monoclines are large step-like folds in otherwise horizontal sedimentary strata, and tabans as blocks of basement rocks are displaced upward. The ductile sedimentary strata drape over them. We'll see that in the picture, so understand that. So here we have dome. So we have two circular shapes, but this is dome, and this is basin. Dome, if we look at it, we'll find older rocks at the center and the tip of the strata always going outside, pointing outside, away from the center. Basins, the opposite. Younger strata at the center, here, and always the depth pointing towards the basin center. If you look at this, we have older strata here, and then as you go away from the center towards Y or X, you find younger strata. And this shape, the circle shape, is a dome. This is the Black Hills of South Dakota. We have another circle shape here, but in the middle we find younger, and as you go out you find older strata, and the depths, the strata going towards the center. This is a basin, which is Michigan Basin. Monocline. This is a monocline from Arizona. If you look at the figure here, we have fault, and this is basement, and the sedimentary layers were horizontal, but as you go down here, you'll see the sedimentary packages just draped and bent, depicting the topography of the basement. And this is what we call it monocline, because it just has one limb, one side, and the rest is just horizontal. Now faults. So we finished faults, which is the ductile deformation, and now we're going to faults, which is brittle deformation. Faults and joints, rock structures formed by brittle deformation. That means we have fractures. We have something broken, rocks broken. Faults are fractures in rocks along which displacement has occurred. So to say there's a fault, we have to have two things, fracture and displacement along that fracture. So layers moved up or down along that fracture. If there is no displacement, we call it just fracture. Okay? And earthquakes happened along these faults because of their sudden movements, just energy released along these fault lines. We have two types of faults here, dip slip and strike slip. Dip slip, that means the movement along the depth of the faults. Okay, dip slip faults occur when movement is parallel to the inclination, which is the dip direction. We have the hanging wall and the foot wall. The hanging wall is the rock surface above the fault. The foot wall is the rock surface below the fault. We'll see it in the figure. The vertical displacement along the fault produces long, low clefts called fault scarps. We have also vertical, not dip slip, or neither dip slip nor strike slip. We call it vertical displacement. But we'll look at the hanging walls and foot walls. So as we said, we have dip and strike for any fault. If the movement goes up and down along the dip, we call it dip slip. If it happens along the strike, we call it strike slip. So let's look at this. This is dip slip fault. If you have a tunnel here along the fault line, where your foot at, this is what we call it, foot wall. Where you're hanging your light or your jacket, this is the hanging wall. So the hanging wall, the surface above the fault, the foot wall, the surface below the fault. Okay? And by the way, this fault is reverse. So let's look at the normal fault here. Normal fault formed due to tension. So these two parts going away from each other along the fault line. And here we have the hanging wall above the fault line and foot wall below the fault line. And as we see layers, for example, this orange layer, it's the same orange layer here, but along the fault line, this one dropped down. So this is normal fault. Layers just dropping down. The hanging wall dropping down, slipping down along the fault. This dip slip, normal fault. Okay. Faults and joints, as we said, rock structures formed by brittle deformation. Dip slip faults. Normal faults are characterized by the hanging wall moving down relative to the foot wall, associated with tensional stress as the rock pull apart. Okay, so if we look back here, there's tensional stress, not compression, tension. And the hanging wall drop moving down relative to the foot wall. Okay, foot wall looks like going up, hanging wall going down. So large scale normal faults are associated with fault block mountains. Yeah. Example basin range province. So we have uplifted blocks are called horsts, and down dropped blocks are called gravens. So we have fault block mountains, and we have half gravens, which is tilted fault blocks. And then we have another feature we call detachment faults, represent the boundary between ductile and brittle rock units. We'll look at the figure and find them. If we look at this figure here, we have parts that pushed up and parts that dropped down. And these all normal faults. So this is a graben, and this is the horse. Graben, horse. This half graben, by the way. But this is full fault block mountain. Has graben and two horse at the side. Here we have just faults from one side, normal faults from one side. And these normal faults attach it to one long fold. This is what we call detachment fault. Above this detachment fault, we have brittle deformation faults, but under it we have ductile deformation, mostly folded. If you look at these fault block mountains, here we have horse lifted up and grabens drop down, this flat one here. Dip slip faults, now reverse. Reverse faults are characterized by the hanging wall moving up. This is the opposite of the normal faults. So hanging walls moving up relative to foot wall, associated with compressional stress. So it's exactly the opposite. Normal faults, hanging wall moving down, and they are extensional forces. But reverse faults, hanging wall moving up, and crustal shortening. So reverse faults will lead to crustal shortening. And we have another term, thrust fault, have an angle less than 45 degrees. So the overlaying plate moves almost horizontally. So thrust fault is just a reverse fault with an angle of less than 45 degrees. Okay, most pronounce it, these faults, reverse faults, most pronounce along convergent plate boundaries, like Glacier National Park. So they happen along convergent boundaries because you need compressional forces. So let's look at this. This is the fault plane. Above the fault plane, we call it hanging wall. And under it, we call foot wall. So if you look at this layer here, it's exactly the same. So this layer is going up. So we know the hanging wall is moving up. This is reverse fault. To have this configuration, you have to have compressional force. And that means there's crustal shortening. And this one we call reverse fault because the angle here is above 45 degrees. The angle between the fault plane and the horizontal, more than 45 degrees. But if the angle is, this is still reverse fault, but the angle is less between the fault plane and the horizon, less than 45 degrees, we call it thrust fault. And it's still compressional, still reverse fault, but the angle less than 45 degrees, we call it thrust fault. Now we go to the other type of faults, strike slip. So we said the movement of the rocks can happen along the fault dip, we call the dip slip, or along the fault strike, we call it strike slip faults. Strike slip faults are characterized by placement that's horizontal and parallel to the strike of the fault. Types of strike slip faults: right lateral and left lateral. Right lateral, as you face the fault, the opposite side of the fault moves to the right. Left lateral is still strike slip. We call it right lateral strike slip, left lateral strike slip. As you face the fault, the opposite side of the fault moves to the left. I'll explain this in the figure when we look at the figure. Large strike slip faults that cut through the crust to accommodate plate motions are called transform faults, such as California San Andreas fault. And we have joints. Joints are fractures in a rock where there has been no rock movement. So the difference between a fault and a fracture has no movement, just breakage in the rock without movement. And most joints appear in parallel grooves. So let's look at the strike slip faults. So the rocks moving along the strike of the fault. And as we said, we have left lateral and right lateral. So if you are standing up here and looking at this side, okay, and look at that block. If it's moving to the left, that's left lateral. If it's moving to the right, that's right lateral. So this is moving to the left, left lateral. If you're standing here and look at this side, you'll find it moving to the left, so left lateral. The opposite is right lateral. And here, if you look at the drainage pattern of the river, and when it comes to the fault, it bends like 90 degrees, and then it comes back 90 degrees here. So that means there's a fault when you see like drastic shift in the river pattern or stream pattern. That means there is a fault, and this is, we call it offset. Fault offset. And here joints along the rocks, and these joints just look like parallel to each other, but there's no movement along these joints. Now, mountain building. Mountain building has occurred during the recent geological past. So we have recent and older Paleozoic age mountains. Older ones. So what's the recent mountains? American Cordillera, the Alpine Himalaya chain, the mountainous terrain of the West Pacific. There are three. And old Paleozoic age mountains, we have the Appalachians and the Urals in Russia. These mountains are deeply eroded, the old ones, and topographically less prominent, but the young ones, topographically very prominent. So we have a term called orogenesis. Is the process that collectively produce a mountain belt, orogenesis, which is mountain orogeny, yeah. So if you look at this map, we have young mountains in a brownish color. So this is the Alps, Atlas, Caicos, Zagros, Himalaya, all these mountain chains connected, and they are young, same mountain chain. In here we have Andes Mountains, and we have North American Cordillera, those young mountains, less than 1 million years ago. All mountain belts, these magenta colors, like Caledonia, Urals in Russia, Caledonia in Europe, Appalachians in America, North America. And we have more here. shields. Shields like African shield, the yellow ones, Brazilian shield, Australian shield, and Baltic shield, Greenland shield, Canadian shields, and we have stable platforms, the grayish color. Stable platforms are shields covered by sedimentary rocks. Like here, North Africa, we have stable platform, just shields covered by sedimentary rocks. We have a lot of stable platforms, stable platforms, stable platforms, always surrounding the shields. Okay, mountains that display faults and faulted and folded rocks are compressional mountains. So this is a visual evidence that there's compressional forces working on these rocks. And here they are saying plate tectonics provide a model for orogenesis, which is mountain building. And there's a note here, Earth's major mountains have formed along convergent plate boundaries. So mountains, they form along convergent boundaries. Subduction and mountain buildings. Subduction zones are zones of convergent boundaries. We have island arc type mountain building. We have Andean-Type mountain building. We'll read them, but when we look at the pictures and figures, will be way easier to understand them. So, island arc type mounts results from the steady subduction of oceanic lithosphere. And all of these models just subduction, but they are different models. Continued growth can result in the formation of parallel mountainous topography, consists of igneous and metamorphic rocks. Okay, so we have subduction. Andean-type mountain building, subduction beneath a continent rather than oceanic lithosphere. Exemplified by the Andes Mountain. It starts with a passive continental margin, thick platform of shallow water sedimentary rocks, and then eventually the forces that drive plate tectonics change direction and subduction zone forms. Oceanic lithosphere must be dense enough to sink. So let's look at the Andes-type mountain building. So what we have here, we have oceanic crust, subduction zone that's subducted under continental crust, and then partial melting happening, and we have plutonic rocks came up, and that causes uplifting and igneous activity. And here we have accretionary wedge, which is deformed sedimentary packages due to pressure. And then after a while, what happened? These accretionary wedges due to pressure, they are uplifted. And then the batholitis or the igneous, these mountain ranges uplifting and erosion exposed batholiths consisting of numerous plutons. So this is the Andes Mountains. So basically the idea, you need subduction zone. Okay. This here we have example of oceanic and continental crust. Collision mountain belts, Cordillera type mountain building associated with the Pacific Ocean, meaning it's unlikely to close. Subduction zones may form island arcs. If you have island arcs, that means you are dealing with two oceanic crusts that will eventually collide with continental crust. The collision and creation of small slivers of continental crust from the mountainous region that rim the Pacific. Terrains, crustal fragments of exotic material, that's right, make up much of the western United States. So if we look at this here, collision and accretion of a small crustal fragments to a continental margin. So here, starts from here, A, B, C, D. If you look here, we have microcontinent, we have, this is a oceanic crust, and here we have continental crust, and we have subduction zone. And here basically we have island arcs within the oceanic crust, and we have subduction zone, trench, and then what happens? This island, or these island arcs, created accretionary wedge stacked to the continental crust, this pinky color here. And the subduction is still going on. And the third stage here, another subduction happened due to the pressure and the compression. So we have old subduction, and here the second subduction zone, and the conversion process kept going, and this ocean getting smaller and smaller until this microcontinent collide with the mainland or the main continent, and it created mountain ranges. Okay, so it's collision and accretion. So collision, mountain belts, and we'll keep going here to show you the examples. So there is also these collisions and accretion. Here we have oceanic crust, this orange reddish color, okay, inside the continent. This is North American Cordillera, and it is deformed by the accretion of terrains here, the blue ones deformed. But it's very weird and strange to find oceanic terrains inside the continent, and the explanation for this is this process, which is collision and accretion of small crustal fragments to a continental margin. And you have collision and mountain belts, Alpine-type mountain belts, continental collision. And the zone where two continents collide is called a suture. Okay, typically contains slivers of oceanic lithosphere. Most compressional mountains exhibit the deformation of a thick sequence of sedimentary rocks called fold and thrust belts. And we have the Himalaya as example. So we have the Indian continent here on the left, and we have the Asian continent on the right. This oceanic crust and this continental crust and continental crust. And there used to be a subduction zone here between. There was an ocean, and then subduction kept going, and the ocean getting smaller and smaller until these two continents, the Indian and the Asian, just collide, in all the sedimentary packages and the accretions in the middle just compressed and deformed and formed the uplifted formed the Himalaya mountains. This is continental collision, formation of the Himalaya, and I believe the Alps too. Okay, now collision mountain belts. The Appalachian, and then the Appalachian tectonic orogeny. So we'll go to the pictures to see it better. This is the first stage, second, third, fourth, fifth. So I don't pay attention that much to the time, but I want you to know the process more. So here we have North America and Africa. And here we have tectonic volcanic arc and a Valonian microcontinent. So what happened here, the first stage? We call it tectonic orogeny, where these volcanic arcs collided with North America. Okay? And then we had double subduction zone. We have one, two, and here we had double subduction zone, and the Avalonian collided with North America and formed Acadian orogeny. And then another subduction zone grows here, and the whole African continent collided with North America and formed the Alleghanian orogeny. And that was like 350 million, 250 to 300 million years ago. And then after that, the divergent boundary formed in the Atlantic Ocean developed. And all of these old orogenies now just went through the process of peniplanation and flattened. So this rifting started 180 million years ago, and Africa split it away or split apart from North America. Now what causes Earth is varied topography. Why the Earth has different topographies. This is the principle of isostasy. Less dense crust floats on top of the denser rock of the mantle. So we have crust, light crust floating above the mantle. And we know we have the lithosphere, which is the very upper mantle plus the continental and the oceanic crust. That lithosphere floating above the mantle. It's very light and floating above the mantle. Isostasy is the concept of floating crust in a gravitational balance. And the example here is the floating of various sizes or different sizes of floating blocks on water. How is isostasy related to change in elevation? This is the main goal here. If weight is added or removed from the crust, the lithosphere, isostatic adjustment will take place as the crust subsides or rebounds, subsides down or rebound uplifted back. Crustal rebound is present in Canada's Hudson Bay region following the melting of ice sheets in that region. So when there was an ice above that region, the region just subsided down due to the weight of the ice, and then after the ice melt away, the land just rebound or uplifted up again. So here we have these blocks. The biggest one is all of these floating in the water, as if it's like the crust. These represent the crust just floating on the mantle, above the mantle. When you have thicker blocks, these thicker blocks will have deeper roots in the mantle. The smaller blocks will have they'll have like smaller roots down in the mantle, but lower elevation. So effect of isostasy. Here, if we have compression, especially in the mountain building region, subduction zones, what will happen? Compression and uplifting at the top side, and due to the weight, we'll have here subsidence. So the whole lithosphere is lighter than the mantle and is floating above the mantle. Let's say erosion, over time erosion happened and this mountain lost a lot of its elevation and weathered and transported to the ocean. So here we'll have sinking, but on the other side we'll have isostatic uplift or rebound. The crust will start uplifting up until it goes back to the normal situation. So these effects or isostatic adjustments. What causes Earth's varied topography? The principle of isostasy. How high is too high? As mountains grow, gravity acts on the warm and weak rocks inside the mountains. Eventually, the gravitational forces are so large that the rocks will flow laterally. I'll explain this. This ductile spreading and consequential subsidence is called gravitational collapse. Yep. So, as we said, when we have mountain building collision, what happened? Rocks will be uplifted, and the roots of the mountains will go deep down, cause subsidence. But over time, when we lose those compressional stresses and the mountain lifts on its weight, what will happen? The mountain will start collapsing on its own weight and subside and spread away from the center under its own weight and the gravity. Also, the mountain at the bottom will start the process of uplifting or rebound, and the weight of the mountain will be spread on both sides. We call it ductile spreading, and the whole process we call gravitational force or gravitational collapse of the mountains. So at first here we have compressional forces, but over time will be extensional forces due to the gravitational collapse. And by this, we came to the end of this chapter, the mountain buildings, and we'll get 3 minutes rest with the national anthem of Sri Lanka State. Thank you very much.